first, I'd like to just kick things off by giving Don and Michael a chance to introduce themselves and their company's missions. So maybe start with Don here.
Yeah, hi, my name is Don Fahey. I'm a principal quantum scientist at Quantum Catalyzer, which is an incubator-style company that focuses on commercializing and transitioning quantum sensing technologies from the lab to practical sensors, with a start mostly on nitrogen vacancy sensors and diamond, but we're also looking at other sensor platforms as well. One of our subsidiaries is Euclid, which won the pitch competition yesterday, or 2 days ago. So you may have, if you haven't heard about them, check them out for sure. But my background has been in quantum sensing for 16 years, focusing on things like Rydberg sensors, both in ultra-cold atom systems and warm vapor cells. Spin squeezing at the fundamental limits of sensing, trying to get that Heisenberg uncertainty limit, scaling. And then more recently looking at solid-state sensors, things that don't require a massive lab, but they could be miniaturized and scaled down, hence NV sensors in diamond, Rydberg sensors and things like that as well. So that's what we focus on at Quantum Catalyzer, and that's what I'm most interested in.
Great, thanks, Don. And how about you, Michael?
Hi, everyone. Apologies for just introducing myself again if you've been here before, but I'm Michael Hush. I'm the chief scientist at Q-CTRL. So at Q-CTRL, we basically make quantum devices work. So a lot of our work is with improving the performance of quantum computers. So as an example, if you want to use IBM's devices, you can go to IBM today and click add Q-CTRL into your quantum functions solution, actually. It just got launched today. But that changes the device and eliminates a lot of those errors which would normally prevent you from getting the right answer. And we do that using error suppression technology, which deletes the errors, let's say, before they even get into the actual problem, before they cause a problem at the end of the chain. That same physics and technology that we use to improve quantum computers, we also use to improve quantum sensors. And so we also have a program focused on navigation, navigation without GPS, that is achieved by using cold atom sensors that measure very precisely changes in gravitational fields and changes in magnetic fields.
Great, thank you. So I thought I would kick us off here by just asking, what are quantum sensors? How can we define quantum sensors? And for the sake of clarity here, maybe I'll start with Michael. Do they need entanglement?
No.
Very good.
Entanglement's one of my favorite topics because I think it is it's the biggest distraction. It's not the fundamental piece that's important. The really important thing is coherence, which is another fancy word. So I don't think that helps anyone in the audience. But I think for me, the best way to think about it, the thing you have to make it more tactile is lasers. Lasers were one of the first new quantum technologies. And lasers have this special property that if you shine light, it's all going in one direction and it stays very intense for a long, long way. And that's because of this idea of coherence. All the atoms, all the photons that are ejected from your laser are moving in the exact same way. And so what's special about this new revolution in quantum technology is we're using that same property of coherence, but we're using it on individual quantum systems. So the quantum sensors that I'm building in my labs are all based on individual atoms, rubidium atoms actually. So the quantum property is that we exploit the coherence of those atoms between two transitions. And in practice, what that means is because you're using an atom and a laser, it means that your measurements are connected to a fundamental constant. They're based according to the laws of physics, which are the same here, it's the same on Mars. And so that allows you to use a quantum sensor without calibrating it. You don't have to worry about it changing shape because of temperature, because an atom and a laser is the same everywhere. And that's the key advantage quantum technology gives in the quantum sensing space, is it's able to be compact, often low power, and calibration free.
Yeah, I would just build on that. That's a really great analogy. Oftentimes, classical sensors are thermalized in a sense. All the sensing components are randomized, in quantum systems, you can polarize them and get a major amplification of its response to stimuli through that process. So, as an example, rubidium atoms in a vapor or nitrogen vacancy spins in a diamond, by shining green light on them, in that case, you can polarize them almost to 100%. And now you have, instead of a very small difference in populations, you have a massive difference that responds much more strongly. I think there is this general sense that as you said, quantum sensors use quantum phenomena. One example of that are discrete energy levels, coherence times, and things like this. There is a lot of talk about entanglement. There is a lot of talk about that in the future. And I think that it is true in the future. There's potential to exploit that entanglement to surpass what is called the standard quantum limit. Maybe it should be called the classical limit, right? If you actually can remove all the technical noise from your system and you have just whatever the sensing state is, classical systems are ultimately limited by uncertainty principles. But in a quantum system, you can play tricks where you offload uncertainty from one variable to another, the one that you don't care about. We're not there yet. Of course, we can do this, but it's not providing always an advantage because right now the technical noise is usually too high. But that's not to say that in the future this won't be the case. As systems improve, and if you invest, for example, in quantum sensors now and in the future, we could get there someday. I also just want to add that quantum sensors have been around for a long time. If you think about the laser, for example, or if you think about NMR or CT scans and things like this, these are all examples of quantum sensors. Even atomic clocks from the mid 20th century, vapor clocks and things like this. So we have a long history of quantum sensors. What do we mean when we think about quantum sensors for the future? Someday it will be harnessing that entanglement, but I think it's more about expanding the reach of what quantum systems are using, especially when it comes to things that are highly miniaturizable, that can achieve low swap or low C swap, compared to your hydrogen maser, something like an iodine atomic clock or a CSAC, is performing at maybe not a CSAC, but performing at a similar level, but you can now take it on a ship where you can put it in your small device. So I think that's kind of, thinking about where quantum sensors are and where they're going. Yeah, it's an important thing.
Thank you both. Yeah, and you've actually both now called out an advantage of quantum sensors as being low swap C. I think there's often a common, maybe almost a misconception. I shouldn't call it a misconception, but it's vague misconception that the primary advantage of quantum sensors is sensitivity. They're going to give us the best possible sensitivity, and that's definitely true for some use cases. There are some use cases where you really need the sensitivity that quantum sensors can offer. But for the technologies that you're both developing, beyond maybe that swap C, are there other key metrics that you care about that the quantum version of these sensors is really offering?
Yeah, I think it's great to hear you bring that up because it causes a lot of confusion. Because often we get approached by people who are just like, well, I can't measure this, can you just fix that? And it's not the reality of the situation. So for us, it's swap C is right. You can make things often more compact than it would normally be, but the effect is platforms. So you can get capabilities which would normally only be available in big ships and shrink them down so that you can have them in a unmanned flying vehicle or an unmanned sub, for instance. And that creates a huge difference in what you could do in a mission or what you can do as a company to navigate or explore the area around you.
Yeah. I saw in a talk earlier in Congress this year about thinking about technologies that are expanding our sensitivity or improving upon already established modalities or devices, but then also sort of truly disruptive things. And I think when you talk about, for example, a truly vector magnetometer, that's a new modality. It's offering something that we didn't have before. I think another example would be, it's a little counterintuitive, but when we think about quantum, when many of us think about quantum, we think about very delicate systems that, maybe, especially in previous years, you'd had to get very cold. Maybe you have to use cryogenics to achieve. But there are examples where you can access the quantumness in material, like in diamond, for example, that is isolated from the thermal environment. And you can hyperpolarize it. It can still be sensitive in the way that you want it to, and you can manipulate it. So I think unlocking this sort of potential allows you, for example, to go into even counterintuitively, more extreme environments. So maybe a diamond is a very hard thing that could go into a very hot environment, for example, or something of extreme radiation. So it's not just achieving better sensitivity, it's not just achieving better swap C, but also I think unlocking new forms of sensing that weren't available to us before.
Excellent, thank you. Yesterday we saw Dr. John Burke give a talk where he listed, the U.S. DoD's top priorities in quantum, and 3 of the top 4 were in quantum sensing for positioning, navigation, and timing, or PNT for short. And maybe for anyone who was not here for Michael's talk, Michael did provide a great overview of what that means, but can you just give maybe a quick recap of what is complementary PNT and how do quantum sensors fit into that ecosystem?
Yeah, so basically there are a variety of challenges that we would face if we lost access to GPS. And defense is particularly concerned about that because if there are many ways in which we could lose access to APS if we were in conflict. And that reliance on GPS that has been produced not only does affect potential defense missions, it actually is fundamentally a part of even how we trade stocks, for instance. The timing that GPS provides enables people to correctly trade at the right time. So it's really built into the fabric of society. And what we're doing at Q-CTRL is we want to remove that vulnerability. We want to create an alternative solution that you can rely on and sometimes even determine if your GPS signal has been spoofed, for instance. And so we do that using these quantum sensors, which can provide you basically a very difficult to spoof reference. For instance, when we make incredibly precise measurements of gravitational fields, we can use that when combined with a gravitational map to find your location. And if someone wanted to change that gravitational map, they would have to move a mountain, which is extremely challenging. So that ability to produce another reliable source of truth for your location is critical, very much in the defense context, which was really highlighted yesterday, but also in the long term will have some implications in the commercial sector. I often think about autonomous vehicles as being one of the next potential opportunities where you could see quantum sensors having a real effect, where they need to have a variety of ways in which they can locate themselves reliably and not be spoofed by people who might buy some GPS signal spoofer off the internet for $100. There are a lot of ways in which we want to improve our resilience to navigation vulnerabilities.
Indeed, and there are also environments where GPS doesn't work as well, like underwater or maybe in a busy city center. I think you can, if you just look at the arc of quantum sensing and sensing in general, in the 20th century, you saw a lot of maybe what we now call a quantum sensor focused on scientific investigation and maybe the medical community, like I mentioned, MRI and NMR before, or CT scans. Now there is indeed a lot of focus on PNT. I think that if you look at what sensors can sense, position, timing, navigation, looking at magnetic fields for magnetic navigation, looking at gravity, gravimetry, and looking at timing. All those things are essential, not just to GPS, but GPS-denied systems going forward. And so if, where are quantum sensors going right now? I think they're mostly focused on those areas. So you see a flourishing of magnetometers, various types of magnetometers, of electric field sensors. That's more related to communication, gravimeters, and atomic clocks, and other types of clocks as well.
I did want to also, since we're talking about defense often comes up with sensing. And I wanted to kind of give a bit of context there from our experience of why that's so important. So it's that cost thing we find. So in principle, quantum sensors could be quite cheap. But today they're not. There's a lot of research still to be done. There's a lot of ruggedization still to be done. And in the sensing commercial side, what we've tend to find is that it needs to be very cheap. It needs to be at scale for a sensor to have an impact in the commercial market. So what you're seeing is the defense is able to invest more on very specific but sometimes expensive navigation capabilities. And they, at the moment, I think, around the world are really the #1 investor in quantum sensing technology. So that's for us at Q-CTRL in particular. So we're located in Australia and the US. But one of the most important things we think that the world really needs to, well, particularly between Australia, the UK, and the US, the AUKUS framework. Having these frameworks where you can have development between nations with similar values is so critical to pushing these technologies forward. Because we're seeing such a pull for these technologies in the defense space, and we need to ensure that like-minded nations can work together to achieve those common goals.
Thank you. And you both have deep expertise in magnetic anomaly aided navigation, or what we call MagNav for short. And Michael, you mentioned the appeal of quantum magnetometers as having this prospect of being very low cost, very cheap. But we do have this big barrier ahead of us of creating magnetic maps with sufficient spatial resolution and at the right altitudes. And that is going to be extremely costly. So Don, maybe could you say a few words about some of those challenges related to magnetic mapping, and what are some of the big barriers facing broader deployment of these technologies?
Sure. Yeah, this is definitely a hot topic right now. From the geo and paleo perspective, there's actually been a lot of work on this, over the years, and I think more recently now there's been more of an effort to make these world magnetic maps, including some both national and international incentives. And one of the things that you mentioned is resolution. So a lot of the magnetic maps we have are from satellites. There's been ESA more recently put out a satellite system that has been mapping Earth's magnetic field. But when we talk about MagNav, we're not talking as much about the global Earth's magnetic field, which fluctuates. We're talking about usually the lithosphere, so crustal variation. And that's where you need this high resolution. That's where you're going to have the most effective MagNav capabilities. And what we have right now is, depending on who you're talking to, various levels of resolution in total field. There are efforts to improve that resolution by going out and getting ground truth. But also we need sensors that have, if you want to do navigation, have the sensitivity you need, although it doesn't have to be outrageously sensitive, right? It just has to be good enough. So that's about a nanotesla RMS or so, maybe a little bit better. But you also have to have a stable baseline. So it can't be drifting. Otherwise, this is something that will lead you astray. And it probably needs to be tied to an inertial navigation system, to an INS system. And in fact, these engineering problems are some of the most significant ones, is how to tie these systems together. This may be something that you've thought about. But I will say one more thing about this, which is that when I talked earlier about new modalities, new changes that are just different than improving upon, one of those is vector magnetometry. So if you have 3 components at every point on Earth's crust, you have more information to sense with, and you can more quickly identify where you are and where you're going. Our maps to date are mostly total field. Now you can do fancy interpolation things to convert those to vector fields, but we need a world vector magnetic map. So that's, I think, at the moment, a major challenge that needs to be accomplished. But also, once you go to vector, you become more susceptible to rotational error, motion, and inertia. So that's where that pairing with the INS system becomes more and more of a challenge. Right now, people are working on this. Someday, perhaps we'll have sensors maybe in vapor cells, maybe in NV diamond, where you can co-locate. You can use the same medium to both do a gyroscope and do a magnetometer. That would be outstanding. But at the moment, we have to overcome these early engineering hurdles. Yeah.
Thank you. And so Michael, you have started testing a lot of these technologies on relevant platforms, magnetometers, inertial sensors, gravimeters. But of course, there's a big leap between testing these technologies on a relevant platform and making them readily available for broad deployment. So can you say a little bit about what needs to happen before, for example, Q-CTRL would be ready to fulfill an order for 500 of these, for example?
Yeah, I think these demonstrations that we've been doing on platforms, they are really hard. It is difficult. So there is a lot of maturity in previous sensing technologies in the way they are manufactured and the way they're packaged, which sometimes doesn't exist for these newer technologies. So they use cold atom vapors, And there doesn't really exist a standardized approach to putting these devices together in a manufacturing scale. So those are some of the initial longer term challenges, is like figuring out how you can make these sensors at scale in a robust, ruggedized way, which is packaged. But in the meantime, when it comes to making larger sensors, which are not necessarily for mass volume, but for small volume, which is what we're focusing on now, the biggest challenges there is just ruggedizing them so that when a platform is under motion, your sensor just doesn't stop working. And there is surprisingly very little research on this topic, because a lot of experimentalists and labs don't like just shaking their equipment, obviously. So that's where we've been really innovating the most, is really like how you can get a quantum sensor to operate when it's under motion. And that's where we're really focused on developing our software, which honestly we are happy to sell to anyone making a quantum sensor. So we have a full stack solution, but we actually compete in any part of the stack which anyone wants to take advantage of. So we already are working actually with another defense prime with another cold atom sensor, where they're taking our software, but they're providing the hardware. And that's another modality which we're more than happy to work with people in.
I would just add to this in general, thinking about the leap from optical table or the lab to deployable, maybe mass produced. That's, in some ways, that's one of the hardest steps, is to make that leap. And it takes a lot of hard work, and it takes investment, and it takes time, and it takes money. I think sometimes people think, oh, well, this thing is working on this person's fancy lab. Why can't we just box it up and build, just get a bunch of people and build 500 of them? And it's not that simple. If you look at historically what has worked, you're talking many millions of dollars of investment and years of work to take something from the tabletop into a really portable and mass-producible and practical sensor. I'm thinking about, for example, more recently with atomic vapor optically pumped magnetometers. You have twin leaf and Q-spin and geometrics, and that's now 10 or 15, 20 years into maturity. But it really took years of investment, largely from the government, and I would really emphasize that this is a government security track, through SBIRs, through DARPA, DIU programs, or programs connected to the DoD labs that really made that possible. And it would not have been possible without that type of long-term, continual investment through what feels like kind of a hard, unproductive time, but then the result is something that's extremely useful. OPMs are the most sensitive, portable, low-cost magnetometers that we have at the moment. That's not to say that other modalities won't someday get there with that type of investment. I'm also thinking about, hyperfine is another example with mobile MRI. This is another example of something that takes 5 or 10 years to take from the lab to something that you can wheel up next to a patient, or even longer. So these, I think, you need government, or you need long-term stable investment that can also come from some of the large players in the DoD sphere. So we're talking like the big companies that have that type of long-term investment, long-term institutional infrastructure and outlook, working together with small companies, with companies that are innovating, that are maybe the professor who's the leader in the field is involved, and so you can have that type of very fast innovation paired with some sort of stable funding and support for a medium-term return. Yeah.
Excellent, thank you. And since we spent quite a bit of time on MagNav here, Don, I wanted to ask, can you quickly highlight maybe some other applications of magnetometers?
Sure. Well, you mentioned gravity, so that's and related to gravity is, and you can do gravity in a couple different ways. You can do atom interferometry, very fancy. You can also just use a very good clock, and you can look at time dilation, going back to Einstein. And so clock development has seen some interesting turns in the past 20 years. With chip-scale atomic clocks, there was a major effort in the early 2000s up until now, resulting in commercial devices from Microsemi and Teledyne. These are excellent systems. They don't have the sensitivity maybe to do gravimetry, but they are good for, say, jam resistant GPS receivers and things like this. The cost on those systems are still relatively high, and they need to come down for that to be more useful. But when it comes to clocks, you have also, I mentioned Vector Atomic developing their latest clock, I think is the iodine-based atomic clock that is competitive with the gold standard hydrogen masers, and yet it's rack mountable and has been deployed in sea tests, as I understand it. So those are some examples of that's sort of in the timing sphere. I believe there's also a company called SciTime who's developed a MEMS-based clock or oscillator, and so there's timing. And then let's see, inertia, which is related to gravity. And then also there are other things too, like electric fields. So Rydberg sensors. Rydberg atoms are highly excited atoms. Oftentimes there are things like rubidium or cesium. You can use other things. They're very sensitive to environmental parameters, especially electric fields. And so people have been trying to find ways to find uses for these extremely sensitive electric fields, especially in the sort of antenna and communication sphere. I know that there are some companies like Inflection and Rydberg Technologies through the DARPA Quantum Apertures program that have been developing that type of thing. Not quite sure that there's what the product on that end are at the moment, but so there's electric fields. And then there are other areas too, like I mentioned earlier, sort of more in the medical community. You can imagine NMR, better NMR for chemical detection, molecular detection. Subatomic particles for nuclear science, temperature and pressure. But as we've been talking about, PNT is really where quantum sensors are right now.
Great, thank you. And Michael, earlier, since we only have a few minutes left here, you called out the value of AUKUS for your work. Can you speak a little bit to the value of collaboration that you've experienced?
Yeah, so there's like it's almost the people aspect as well. So Q-CTRL was founded 6 years ago. Michael Biersick, Professor Michael Biersick is our CEO. He was a lecturer in Australia, but he actually did most of his career in the US. And so I've always found at Q-CTRL combining that US ambition with the Australians, I think, give more of a ability to get things done with much less. And that combination can be really powerful. It's certainly been a driving force behind Q-CTRL. So not only in just that cultural sense, but then in a very practical sense, like there are often very aligned goals with our defense initiatives between nations. And for those to be effective, it really is important that we're able to co-develop technology. Australia has made massive investments in the development of fundamental science around quantum technology, and we have some phenomenal science and companies developing in Australia. The AUKUS framework is a real opportunity for the US to leverage those great scientists and to create technology which is aligned with both nations' interests.
Thank you. And Don, can you speak to any collaborations that have been valuable in your experience for developing some of these technologies?
Sure. Well, one is actually in the imaging space. So one I didn't mention outside of PNT is actually quantum sensors for imaging, say, magnetic fields. This is something that our company, Quantum Catalyzer, has focused on greatly. Diamond nitrogen vacancy centers work wonders in maintaining spatial resolution, but also high magnetic sensitivity. And you can use these in wide field microscopes, or you can pair them with, here's an example, with atomic force microscopes. You can put an NV center on the scanning tip of an AFM and scan it around. And that type of collaboration has led to Q-Saber and Qnami's innovative microscopes that can create magnetic maps on very small length scales. But in something that's pairing with, outside of PNT, the future of quantum sensors and getting into the smaller scale, well, actually big in some sense, you have looking at chips, semiconductor chips. So, obviously we have the CHIPS Act, here in the US, a huge push to develop our own chip capabilities, and failure analysis, understanding when chips are not working, why they're not working, and having better tools for seeing that is essential. Actually, in a related space, also batteries. Batteries power everything that we do, especially anything portable, and making better, smaller, longer lasting batteries is an essential thing. These these quantum microscopes create these magnetic maps that allow you to see if there's a short or an open in a system, understand what's going on, or just do straight up failure analysis. And that partnership between small companies like Quantum Catalyzer and Euclid and these large companies that have for years been creating chips or batteries is essential to moving both things forward and improving that workspace.
Great, thank you. So we only have 2 minutes. Maybe I'll just quickly ask, for potential end users of quantum technologies that don't yet quite understand the space, maybe they don't even know that they're actually a stakeholder in this space. What would be your ideal vision of being able to engage with someone new, or how might those end users be able to help you maybe with access to test platforms or something that you don't have access to right now? What's sort of on your wish list?
Yeah, I think first and foremost, just come talk to us. So there's just huge value in having a conversation about what your needs are and figuring out if our solution can potentially provide value. I think starting that conversation is definitely your first step. We are often looking for co-investment in development. And so that's another question that you often have to ask yourself is, where are you as a business in terms of, are you looking to differentiate yourself and own some specialized IP around the sensing technology that gives you a real edge? Or are you looking to be more of a consumer when the technology arrives on the market? And the way in which where you see your business and how aggressive it is with differentiation has a big effect on how you interact with a company like us. But either way, no matter what, that conversation and just figuring out where the technology will have an effect on you is going to put you in a better position, whether or not you are investing in quantum technology now or down the road.
Free exchange of information, conversation, feedback is essential, absolutely. I think beyond that, I would also add maybe increasing visibility. So in the quantum sphere, when we hear quantum, a lot of us think about quantum computing, which has very important goals and is moving forward. But quantum sensing is here and now, and has been for the better part of a century, and is going to continue to be that way. So when you talk with people about important markets, you can talk about quantum sensing, focusing on the sensing and the importance of near-term improvements and work in that sphere. So I think increasing that visibility within your networks is one way that end users who maybe aren't in a position to invest or support in other ways right now can actually really help with this field.
Excellent, thank you both. Please join me in thanking our panelists.
Can I ask a question? Okay. From time to time, some people are talking about some pseudoscience like quantum sensing effect of bees or birds. And is there any known biological system using quantum effect to sense environment or whatever?
I don't know that I can answer this question. I don't know that I have the expertise in that particular sphere. But there are lots of areas in the bio world where quantum sensing is going to be useful and has already been useful. And I mentioned some for the medical community. But for example, studying the brain, looking at neuron interactions by real-time mapping. Yeah.
A lot of biological systems decohere way too quickly. They interact with their environments a little bit too much. So I think it may be I have not personally heard of any because I think the interaction with the environment is too strong.
That's one question.
Sorry. Well, please join me again in thanking our panelists.